Hello, my name is O'Neill Wasim, and today I am on behalf of my group mates, Tyrone Rafael Joseph Vargas and Sian Onohdian Nanhay Habibi. I'll be presenting our research titled Predicting Electric Vehicle Adoption, a machine learning approach using socio-economic and infrastructure data. Before I begin, we'd like to thank the host of this ICISS 2025 conference for granting us this opportunity to present our research, and we are grateful for the audience as well as for being here in attendance. First, we'll begin with our problem statement. As the world transitions to cleaner transportation that avoids the use of fossil fuels, electric vehicles or EVs are becoming increasingly more important. But adoption isn't uniform or consistent in many places. Some regions embrace EVs rapidly, while others lag behind. Our research asks which of these socioeconomic and infrastructure factors influence EV adoption in these regions, and can we predict future EV populations using machine learning as well? This is a list of all the previous studies on EV adoption, often focused on consumer factors. First, in the global EV adoption section, Dixit and Singh made a study in India where they attempted to predict whether or not people would buy an EV, and the main predictors shows that it was age, income, gender, environmental concern, as well as the cost of the vehicle, and found that socioeconomic and awareness factors were heavily influenced in the decision making. Then Rubens uh, they clustered potential EV buyers into groups and found that 84 to 94% of respondents in Europe would adopt EVs if the price was below £30,000, which shows that price is a cost sensitivity is a major adoption driver as well. Then there are also many studies for battery and range. These studies included predicting electric vehicle battery health, charging states, and estimating how long a battery would last, estimating the state of an EV battery, showing accuracy and tracking its performance, as well as investigating an EV's battery capacity loss over time, combining multiple models to understand degradation. And then lastly, there has also been studies regarding the charging and energy behavior of electric vehicles. For Random Forest by Shahryar, they forecasted that EVs charging behaviors and demands, which helped optimize the locations of charging station scheduling and locations across the country. And together, these works show that past research has mainly looked at individual consumer behavior, battery or range performance, and charging optimization. However, our contribution is different, focusing on regional level infrastructure and the economy of a county. This is our methodology. For our methodology, we collected data sets from five different US states, which is the Washington, California, Texas, Florida, and New York. All data sets are from 2020 and later, more recent. They are from Kaggle, state registration sites, DMV records, census sources, as well as the US Department of Energy. Then we included four main features from these datasets, which is the electric vehicle population per county, GDP, population and density, and the number of charging stations. Uh, these were chosen because they capture both socio-economic conditions of the county and region, as well as the infrastructure availability. Then we trained four machine learning models, which were linear regression, support vector regression, random forest, and XGBoost. The choice was deliberate. Linear models are appropriate when feature scales proportionally with EV populations, while tree-based models capture complex and non-linear relationships, which could be a potential factor when it comes to including population and density as a feature. This setup has allowed us to compare how well different models could predict EV populations and to test whether infrastructure and economic factors really drive adoption. To process all of this data, we removed missing values, invalid values. We also encountered an issue with counties or electric vehicles being registered by postcodes instead of the counties they were registered in. So we had to match counties and postcodes. We also filtered to only using recent data from 2020 onwards. Older data was excluded to keep the study relevant. And this final data set included 479 counties across 5 US states with a total of 6 features, which were the EV population in each county, the total amount of chargers, GDP, population, land area, and density. Now, to evaluate the performance of the uh, machine learning models, we used an R square score, which is the coefficient of determination. It measures how much of the variation in EV populations is explained by our machine learning model. Then we also calculated the mean squared error, the average of squared errors between predicted and actual values, the root mean squared error, the mean absolute error, and together these tell us how close predictions were to the true EV counts and whether the model consistently under or overestimates. And this is very important later since one of the models often overestimates in counties with lower population, which is a massive trend. Then there's also the Spearman correlation. It determines if the machine learning model keeps track of the ranks of counties and is able to predict the trend of electric vehicle population as well. Then the p-value evaluates whether the correlations are statistically reliable or could have happened by chance. Then lastly, to determine the accuracy of our machine learning models, instead of looking at percentage accuracy, we used a tolerance measure where predictions, if were within 1,000 vehicles, would be considered a true value. Now, the results showed that XGBoost was the strongest performer with an R square score of 0.841 and an accuracy of 89.6%. It has the lowest mean absolute error at around 1,000 vehicles and had also a very high Spearman correlation of 0.932 and also a near zero p-value. Random forest and linear regression also performed extremely well. The only difference for random forest is that instead of an 89% accuracy, it had an 84% accuracy, as well as a slightly lower R square. Linear regression had a 51% accuracy, but still maintained a decent R square value. Despite this, it still showed a high Spearman correlation at, at around 0.841 with a high significant p-value as well, so meaning it is still statistically reliable. The worst performing machine learning model from all 4 models was the support vector regression, which had an R square score of 0.532. After tuning, it reached 83% accuracy, but its errors were larger as well. Its Spearman correlation was 0.886, which was decent, meaning that it was able to keep the order of counties from the highest to lowest population of EVs in a somewhat realistic order. But it still showed that its performance lagged and its p-value showed that the predictions were statistically significant but still weaker. And overall, XGBoost consistently outperformed the others. It had the best accuracy and preserved the rankings of counties and showed strong statistical reliability as well. And for the feature importance, um, charging infrastructure was the single most decisive factor. Random forest chargers contributed 90% of the predictive power in linear regression. Every additional charger was associated with over 30,000 more EVs in the area. GDP was also influential, especially inside of XGBoost, where it had the highest F score, showing that wealthier counties with strong economies adopt EVs faster as well. This tells us that While economics and demographics set the stage, charging infrastructure allows people to be confident in adopting EVs. So, in our key insights that we gathered from this research, infrastructure, counties with more chargers see higher EV populations, as this allows for increased accessibility of electric vehicles. Then, uh, economic strength amplifies the adoption of EVs, since residents and businesses in wealthier areas can afford the shift and renovations to accommodate electric vehicles. Population of counties itself is not enough. A dense county without chargers will not see a strong EV uptake. However, they may have electric vehicles not in public areas, but instead in private residences, in homes, apartments instead. Then the policy and culture of a certain region still matter. So beyond numbers, local regulations, incentives, reduced taxes, as well as like the public attitude towards EVs can either boost or hinder the growth of EV adoption. And for future work, we have some potential improvements to our research, which includes additional infrastructure related features, such as the charger types, where they're located, as well as government subsidies, such as reduced tax, and which of these counties and regions are affected by these reduced tax or incentives. Next, we could also apply model tuning by applying an advanced hyperparameter tuning with and experimenting with polynomial or feature engineering, which could perhaps maybe improve accuracy. Then lastly, we would also like to broaden our data sets. So instead of just having US states, we could include international data, which would make models more generalizable across different economies and cultures, especially in developing nations, in order to capture the scope of EV adoption in its earlier stages rather than in its later stages, just like in the US economy. These steps will make our these improvements will make our machine learning models more powerful and useful to potential policymakers, urban planners, or perhaps manufacturers of electric vehicles who are shaping the future of our electric mobility. So, thank you for your attention. Our code and datasets are also available on our paper for transparency and reproducibility. I welcome any questions. Thank you.